Oh, hang on there, everybody. Sorry about that. Hi, how are you? Good to see you all. See, we have some chatters in the stream. Um, Vaishnavi and um, and Shashik and Simran Sharma. Really good to see you. I'm really glad that you're able to join for the stream. And please let me know if you can hear me and if the quality is okay. That would be really helpful to know that. Excellent. Looks like folks are saying that they can hear me. Thank you for responding there. Yeah, so let me go ahead and send you the link to check in for today. I'm gonna make sure that everybody has this link because it's kind of important to us that you all go ahead and check in. It's gonna really help out on you know helping us figure out which events people are interested in, what kind of content they're interested in, and it also tells us how to give points to your guild. So yeah, this is the website to check in, and we have all of these little check-in links for every event that we run, including our hackathons. So it's just a really important resource to have. But anyway, where is everybody logging on from? What time zones are you logging on from? It's always interesting to see how global of a community we have at Major League Hacking. But yeah, also curious, how has your Global Hack Week been going? Been learning a lot of stuff. What was your favorite workshop so far? Would love to hear from you all in the comments. But today we're actually going to be studying a computer vision algorithm. We're going to be studying something called transfer learning. We studied transfer learning in the last workshop, which was on detecting the ripeness of fruit and how you might be able to do that. But this time we're going to be detecting the sort of ripeness of a plant, or actually the disease of a possible disease of a plant. So we have a data set we're going to be using. I want to show that to you. I'll be sending it to you over the Twitch chat. So please navigate to that link, and it should give you access to our data for today. I had some responses. So it is 1832 in India, or 6:32 for those of us who use 12-hour time, and so that's great. And Germany 1403, so 203. So awesome. So we have morning, afternoon, and evening here in Global Hack Week. How cool is that? Okay, so if you navigate to that folder, it should actually bring you to the plant data set for today. This data set is derived from a Kaggle data set. I'll show you the Kaggle data set as well. Yeah. And someone asked, what is the time there? Here in California, it is early morning. It is just 5 o'clock. Pretty early for Global Hack Week. But in New York time zone, which is where a lot of our MLHer staff is located, it is 8 a.m. So yeah, just morning time here. But yeah, so that link that I sent you over there to the plant disease data set, thank you. Yeah, good morning. So that data set that I sent you is just going to be 3 diseases, And then we have an example of a healthy leaf. So I want to talk about each of these diseases because it's important to realize that they have a big impact. So here's leaf mold. I wonder if you all can see this picture. But this is a picture of leaf mold. And leaf mold is the kind of thing that happens when you have a fungus on your leaf. And it could happen in cooler conditions, maybe darker conditions. And it's really, could be bad for the plant. And so, we want to know, does our tomato plant have a leaf mold? And for those of you who don't know, this is actually a tomato leaf. And has anyone here tried to grow tomatoes? I have. I'll send you a picture. I'll share a picture with you after the break of my tomato plant. But I would love to hear if anyone has tried to grow tomatoes. So Pranav has tried. Did you run into any of these types of issues? I hope not. That would be really bad. Well, not too bad, but it would be unfortunate. Yeah, this is what a healthy tomato leaf looks like. Let's see if it'll load here. You can see there's no diseases on that tomato leaf. So always good to look into our data a little bit before we try to go use that. Now this is tomato mosaic virus. So tomato mosaic virus is another type of sort of plant virus. And so, tomato mold or plant leaf mold was a fungus. Mosaic virus is actually a virus that infects a plant and can cause it to die, basically. Someone says, I've grown chilies. That's really cool. I would love to grow chilies. Is it hard to grow chilies? I don't know. You should let me know if it was hard to grow those, because I would love to grow some. And the growing season is just starting here in California. And Prana says, I only got 2 tomatoes. Yeah, I only got like 4 tomatoes from my tomato plant, and then it died. I'm not a very good gardener, but I'm glad that chilies are beginner friendly too. Good to hear. So if anyone wants a recommendation for some plants to grow, I think tomatoes and chilies seem like some good choices. But let's look at leaf. Finally, we're going to look at 2-spotted spider mite. And this one I think is quite interesting, actually. So this comes from a parasite, a little mite that kind of comes onto the plant and I guess sort of eats it. And the reason why they call them spider mite is because the leaves sort of get this webbing on them. I'll show you. You can see that they get a little bit of a webbing when the spider mites sort of collect on them, and that can cause the plants to die as well. So it's kind of really not. It's good to detect these things. From a monitoring perspective, you want to know, does your tomato plant have any of these illnesses? And so we're going to use this data set today. Go ahead and add this data set to your Google Drive. And then, that's going to be a great way for you to easily have access to this data. So hopefully you're adding that as we speak. But I want to now turn our attention to applying what we've been learning to our machine learning method. And so I have a notebook for you all to look at. And maybe copy into your own Google Drive. So this is a Colab notebook. So you can run it with your Google account. And it's actually basically the same thing as one of the already existing TensorFlow tutorials on flower detection. So we talked about flower detection and fruit ripeness detection last one of these workshops. But now we're going to apply the same framework to our tomato garden. And we're going to be predicting several classes of disease, such as the spider mites and leaf mold and the mosaic virus, and see if we can look at the leaves and tell, is that leaf healthy or not? So let's go ahead and run this notebook. This is a Python notebook, by the way. And you can see each of these cells we can run using the run cell button. So let's click on this run cell button. What we're doing now is actually mounting the drive. So you want to mount your Google Drive. That's going to allow you to access the files in your Google Drive on your Colab notebook. And our goal is to apply the transfer learning notebook to our plant disease data. You can download that data at the Kaggle website, but I also sent the link in the chat if you want to just download this shortened version of the tomato images. Okay, so we're going to talk a little bit about transfer learning, and we are interested in classification algorithms for this workshop. We have had a few lectures on classification algorithms. Last workshop, we talked about them, and actually last Global Hack Week in February, we did a whole video series exclusively on classification algorithms. So if you're interested in that, please go back in our videos. They're all recorded and uploaded to YouTube. But basically for classifying images, the best sort of algorithm to use, one of the best algorithms, is a algorithm called convolutional neural network, or CNN. So I'll type that into the chat. Convolutional neural network, or CNN. And when you are using a CNN, the only problem, it's a highly accurate method. The only problem is that you need two things. You need a lot of images. So you could maybe even use millions of images. And you need a lot of computing power. So as this notebook says, hundreds of GPU hours or more. And, in our data set, the plant data set that we have here, we have a few thousand. We actually also have only about 3,000 labeled photos. And we want to spend much less time. So we're going to use a technique called transfer learning, where we basically take a pre-trained CNN algorithm and we extract features from the images using that algorithm. Then we will train a new layer on top to classify that one. And so someone asked, hey, what are the prerequisites for this? Is it beginner friendly? That's a great question. It is beginner friendly. We're actually not really going to be focused too much on the code. We're actually going to focus more on the process and understanding what's going on. So feel free to follow along. And if you have any questions, please let me know. I'm totally happy to answer those. But I think I sent the research notebook in the chat, and I also sent a link to the data. So you should have everything that you need to complete this workshop. One thing is, of course, there are certain things like the notebook is written in Python. So if you're familiar with Python, that's going to be really helpful to you. But let's move on to the next cell. So we have a setup cell with all of the libraries that we need. And now we have actually our flowers directory, but instead of using our flower data, that the original notebook uses. We're just using plant data, which is this new data set that I sent to you all. There's a few things to note here. There's something called a train fraction. And train fraction is going to be the percentage of the data that is used for training and calibrating our algorithm. And random seed just helps us start off the split between train and test data at some kind of random location. So that way, it's not always giving us the same or a similar split between train and test data. Okay, so that's pretty important to remember, those two parameters here. And then we have this function, make train and test sets, and that's helping us split the data into the train and test sets to get the label classes. So that's exactly what we were mentioning earlier. All of our labels are in different subdirectories. So you have subdirs here. And so we have 4 subdirectories, and we'll have 4 labels. Okay. And so this function returns the train examples, the test examples, and the classes. Remember, you can just run these cells by clicking on this play button here as you go through them. So now we're gonna basically look at these things. So let's click run, and we get some outputs here after the data is split. Normally we would have to download the images in the original tutorial, but this time we have them already in our drive. So the dataset has 4 label classes: healthy, leaf mold, tomato mosaic virus, and 2-spotted spider mite, which gives us 3,687 training images and 925 test images. So you might be asking now, what is the difference between a training image and a test image? All the training images are going to be used to calibrate our model. So they will tune the individual parameters of our machine learning classification algorithm. But the 925 images are reserved for later. So the algorithm does not see those 925 images until later, after it's been fully developed. And we're going to use this 925 data as sort of an out of the bag sample of our data set. Okay. So that's sort of the reason why we split into training and test data set. And I want to just make sure everyone is on the same page. I hope that you were able to see and download the plant disease data, and that you're able to see this Colab notebook and run that. But if you were unable to do that, please send a message in the chat, and I will be more than happy to answer that. Okay, so now let's go ahead and explore the data. So let's click run here. Basically, what's happening here is we're going to show 15 images from the data set. And you can see that, honestly, to someone who does not know about plants, it's probably pretty difficult to classify these illnesses. Personally, for me, it is quite difficult to see which of these leaves has 2-spotted spider mite, which of these leaves has mosaic virus, and which of these leaves is healthy. I mean, this first image looks a little bit like a healthy leaf to me. And then the second image might also look healthy to me if I was looking at them side by side. But that's the beauty of our approach, is it's going to be able to make those fine distinctions. Okay, so now let's run the following code. We have a learning rate, which is going to say how quickly the model should converge on a solution. So if we set the learning rate to be high, then the model will converge quickly. If we set it to be low, then the model will be allowed a long time to converge. And we're going to play with that learning rate today. We also have a pre-trained, what they call TensorFlow Hub module. So this is where we get all of our pre-trained CNN algorithms. And the one we're going to be using to do today is the V2 algorithm. And so let's actually go to this website. I want to check this out. And, and because it's a really interesting place. You can see that the TensorFlow Hub tells us this is an ImageNet sort of model, and it gives us feature vectors of images. And what is a feature vector, you might ask? Well, feature vectors are like telling us what are the important characteristics of the image, and then how prevalent are they in a particular image. And so with those vectors, they have much less dimensions than an image, which has many, many dimensions. And so, yeah, they give you a little bit of a explanation on this, and you can actually explore TensorFlow Hub. Oh, sorry. You can explore TensorFlow Hub over here to kind of get an idea of all the different possibilities with that. Here's the classification right there. That's what we're doing today, and feature vector as well. So if you have a video problem, an audio problem, a text problem, any kind of problem, you might find some kind of pre-trained algorithm in TensorFlow Hub. Highly recommend checking it out. But let's actually go back to our Colab notebook, and we can see that we have several more elements in this cell. So the next element is to pre-process the images into tensors with the size expected by the image module. So we're basically going to take all of the images and ingest them into a tensor, which is a multi-dimensional array. And then we decode and resize the images to make them consistent. Finally, we get our features for a batch of images. And this model is going to be trained in batches. So we're going to show the model a set of images, maybe like 10% of our images first. And then we would expose it to another 10% of the images and see how it improves over the period of time. And this over here is a dense layer, a dense single linear layer. And it's going to be basically communicating between the pre-trained algorithm and our new algorithm. So that's just kind of an intermediary step. But when we have each class of basically, you could say plant disease, model will output some real number as a score of how much the input resembles this class. So that's a really important step as well. We might be able to see which one of these classes has the highest score. And so over here, I'm not really going to get too much into this, but basically they are sort of calculating the probabilities, and then they have a gradient descent optimizer, which is the final layer in the algorithm. And gradient descent, I will show you an example of that. This is a really cool example from Wikipedia. And this example shows you how, starting from some base condition, no matter where you are in the field, you will be able to converge, in other words, arrive at these central points where there is a local maximum or a local minimum. And so that's what gradient descent is going to do is with our features. It's going to take our features and allow us to select the best option from those. Okay, so let's go back to our notebook, and whichever one of the probabilities that is the largest from our different classes, that will be the prediction, right? So then we can compute the accuracy of the model by comparing our predictions with the actual labels assigned to our training data set. So let's press play here to begin with this one. Okay, so what we've done now is just created the model structure and said, okay, well, we'll start with the image model, the pre-trained image model. We'll add the single dense layer here. And now we will put in our gradient descent optimizer at the end. All right, now we're going to move on to training the network. And now that our model is built, we will train it and see how it performs on the test set. So we're no longer going to be using, we're gonna no longer be, designing our model. We're now going to be using data to calibrate the model. And so these three parameters up here, num train steps, tells us how many steps we should take in the training process. And for each batch, we will use 10 examples. And then for each time, we will evaluate every 10. So that's the way we'll test, or train rather. So if you click play, you can see that we start off with an initial result. Should be loading any second now. This is probably the longest process of the whole entire notebook, is to actually train this data because it takes a long time for the computer to evaluate and calibrate according to the thousands of images that we have presented in our training data set. In the meantime, if anyone has any questions, please let me know. And oh, that's a really good question. Someone says, how can we add UI to this? So, UI is, that's a really good question. I think maybe one thing you could try is Flask. I don't know if you know about Flask, but let me show you that while we're waiting for our training to happen. Okay, so I highly recommend that if you are interested in UI for Python applications, maybe like creating a web interface, I highly recommend that you try Flask. This is a basically way to connect your backend to a front end. And let's look at this, for example, a minimal application. You can see that there is a way to host your website, your Python. So we're using Python right now, and Flask could be a really great solution for that. So that's what I recommend, is to check on Flask and see. All right, everybody, we have our first result in from our training period. And and Streamlit. Yes, Streamlit is another very good example. I highly recommend checking out Streamlit as well. So thank you for that suggestion in the chat. But our first result is just 34% accuracy. So that doesn't sound good to anyone, right? It's not even more accurate than basically heads or tails. But our second test is going to be 63% accurate. So we are training on more data and doing another test to see, and we get 64%. And now at step 20, we get 83%. So the accuracy of our model is increasing over time, every single step of the way. And I wonder if all of you, would you be able to do more than, let's say, 87% accuracy on this task? Um, I think I would find that pretty hard, actually. Uh, yeah, I mean, some of those pictures look really similar to each other. Oh, so we're continuing to go along, and we have just 5 more to go. 5 more tests, 5 more batches, in a sense, and that will represent the total training period. Now, the question is, do we want to extend the training period or shorten the training period? Because we could arrive at a convergence. It looks like we may actually be arriving at a convergence for our model already. What that means is that the model's not getting better over time. So we may have already arrived at model convergence. Although there we go, that's a pretty good result in step 60, 91%. Now that's awesome. We just made a big improvement. So maybe we're not actually at convergence yet. And a really small improvement from step 60 to step 70, just a few tenths of a percentage point. But you know, it, it's important to run a long training period because then we can see these overall patterns. Um, and we just have, I think, 1 or 2 more batches, and then we'll be done with our scheduled model training. And it looks like we're going to arrive at a model that's around 90% accurate, which is certainly quite good. And we could see if we might be able to improve that with future tests. All right, so our final model is around 90% accurate, maybe a little bit more than 90% accurate. So that's great, right? But we don't actually know what that entails and where is this 8% that the model is messing up. What we're going to use for that is a confusion matrix. So let me show you what a confusion matrix is, just so that you have an awareness of that concept before we look at an example. Here is the Wikipedia page for confusion matrix. And I think you can see from here that, we have on the x-axis, on these like columns, the predictions of the model. So let's say the model predicts that it's positive for, let's say positive indicates some kind of disease. So the model's predicting a disease. On the y-axis or in the rows, this is the actual condition. So it's possible that the model predicts a disease like mosaic virus, and there actually is mosaic virus in the image, but that would indicate what we call true positive. On the other hand, it's possible that the model will predict positive, but there's actually a perfectly healthy plant, and that would be a false positive. So that's the kind of thing that you can see from the confusion matrix is what is the model predicting? What is it messing up on relative to the actual conditions? So if we go back to our notebook and we run this cell, you can see a layout of which ones are best. So healthy leaves are actually the easiest for the model to identify. There's very little confusion on healthy leaves. Also, the model is not very confused at all. That's two-spotted spider mite. So if you're trying to use this model for identifying two-spotted spider mite, it seems like that's a really, really good use for this model. On the other hand, it seems like tomato mosaic virus might be probably the worst performer of all of them. And you can see it has an accuracy of just 0.8. You can tell that a lot of the times it gets confused for two-spotted spider mite or by leaf mold. So there really are a few of those cases where the model is predicting tomato mosaic virus, but it's actually ending up being something else. Kind of interesting, really, to see that. And then we also have leaf mold, which sometimes gets confused for tomato mosaic virus. So to my perception, it seems like the biggest confusing thing is leaf mold and tomato mosaic virus. Those are really the big confusion elements for our model. And if we could figure out a way to improve the model, we would want to start there probably. I'll show you something interesting as well, which you may have not noticed already, or you may have noticed it. But if we go to our leaf mold data set, this data set, I think, has around, well, I'm not sure actually. I don't think that's going to give us what we want. This has about 300 images in it. And tomato mosaic virus has like 1,000. But two-spotted spider mite has like 1,600 images, and so does healthy. Sorry, I have to sneeze today, I guess. But yeah, the more images we have in a class, generally speaking, the higher the accuracy will be. And we can look at some of our incorrect predictions here as well, where we just visualize a few of those. So this leaf was predicted to be healthy, but it actually had leaf mold. And so that's an example. This leaf was predicted to have tomato mosaic virus or two-spotted spider mite, but actually it had tomato mosaic virus. It's kind of amazing that the model can do such an accurate job of prediction, but it definitely doesn't do a perfect job, and it definitely messes up sometimes. So we could try some other image models. And I actually want to point you to one image model in particular. Which I think would be somewhat interesting to look at. And this is called CropNet. So CropNet is a feature vector model trained on a concatenation of iNaturalist and plant subset of ImageNet 21K. And so if you go down here, you can see this is the link for it. And we can actually replace our image model in the notebook to see if it gives us any kind of improvement. I actually haven't tried this one yet, so we could do it together maybe. You just go to your cell, the one that is titled Build the Model, and replace the link to the feature vector or the MobileNet model, the ImageNet MobileNet, to the CropNet, and we'll save that. So let's try to run this. Let's try to restart and run all. So it should be interesting to see if we get any better result from this one. Oh, thank you for sharing that link to the data set, Ark. And I'm going to share the link to the notebook. I don't think there's anything confidential on there. There's the notebook. Yeah, it seems like we had an error actually. Hmm. Seems like we had a little bit of an error. Not exactly sure why we had that error. Let's see. There's always going to be some kind of issue, right? I think maybe we need to use Keras layer instead of module, but we'll see if that works. We may have to choose a different model from the TF hub in order for this to actually work. If anyone in the chat has any ideas, that is also totally welcome. I love learning from the chat. A lot of times I learn more from the chat than the chat learns from me, I think. Yeah, we may need to try another kind of model. I wonder if we can try another feature vector model. There's one in particular that I thought might be good. Yeah, so what I'm looking at right now is this model here, Inception V3. Because I'm interested in the idea that maybe this data trained on iNaturalist, which is this website that contains like images of like frogs and trees and stuff, could this be a better data set for us? So let's actually try that, because it seems like maybe this would work, this iNaturalist one. Not sure, but we can at least try. And if not, we'll move on to another another thing that we can play with. Let's see, moment of truth. I put in this iNaturalist one. Oh, hang on. Gotta put the change back to module. Yeah, well, it's still not working somehow, but yeah, I wish I knew. I wish I knew why. But anyway, we'll move on to adjusting the learning rate. So let's adjust the learning rate by increasing the learning rate, and we'll see if that creates a better fit or a worse fit. So what we're doing with adjusting the learning rate is we're adjusting how quickly we're going to allow those model parameters to converge. So theoretically, we should see the model go to its highest accuracy earlier in the training cycle. Okay, here it goes. So yeah, last time, if you remember, I think we went from 30s to 60s. It seems like now we're going to the 30s to 70s, but you know, the model is learning so fast that it may not improve too much now after we've had a few training steps. So yeah, but you never know. Maybe the learning rate that we put in there is not going to be that much different. Yeah, it seems like this model is doing just as well as the last one did, actually. Um, it seems like it may learn a little bit faster at the beginning, but yeah, maybe actually increasing the learning rate was a good idea. You know, you never know. And another thing that we can try is to add a hidden layer. So um, this is something that we'll do after now is we can create a nonlinear layer. We'll set our units to 100 and our activation set to this nonlinear activation set. So we will see if that improves the accuracy. Let's see. Okay, so this model actually did not quite get to the same level as the last one. You know, these few percentage points actually do make quite a big difference in telling whether the model is good or not, because it only takes a few extra seconds to train it to make it that much better. But so let's set our learning rate back to 0.01, even though it takes longer, it seems. Okay, and you know, we have our model architecture over here, and we can add this one. So this is our nonlinear layer. So the inputs will also be features, and we could just add 100 layers. Okay, and we will run again and see if we get a different response. You never know. A lot of machine learning work and research involves sort of playing around with the data and seeing if you can tune your model just a little bit better to represent what you're trying to do. I think this may be the last one of the, oh, and we'll try a different optimizer as well. We'll try that after we're done with this. Gradient descent is kind of a simple model, and so the notebook suggests we might try AdaGrad optimizer. That one is a little bit more complicated. So let's see if our model has started training yet. Oh, it already has started training. So it actually started off worse than it was before, but it's quickly getting to the same level that or similar levels that we've been at before. You know, you'll recall our last test ended, it converged at around 88% accurate. This model looks like it's so far at around 87% accurate. We're definitely getting up there. We're definitely getting up there. Yeah, so I think the reason why those image modules didn't work is because we're currently using TensorFlow 1, and a lot of those functions have been since deprecated for certain pre-trained data sets. So yeah, I think that's probably why, unfortunately. But you know, actually, I think I found one that might work for V1. So we will try that after this. All right, so this model, we got about 92%. That's about what we got last time. So maybe, or with our original case. So maybe it is okay to add in a nonlinear layer, but it certainly doesn't seem to really have too much of an improvement in our particular case. All right, moment of truth here. Let's see if this works. Hopefully this works. I'm gonna comment this back out because it didn't seem to really give us too much of an improvement. Once again, iNaturalist is this website where you as a nature photographer or something, you can upload your pictures of nature. So I'll just show you that website real quick. Yeah, so the data, the pre-trained data set now is not just training on one particular thing. It's actually going to train on specifically nature generated images and structures. And so the hope is that it might help us to better find those features, but who knows? We'll see. Let's go back to our tab. This one finally worked. So I'll put the link to that model in the chat so that you all can see it. I'm glad it worked. We'll see if it improves our results, but paste that into the chat if you want to try the iNaturalist model. I think this could have also been useful for our banana ripeness test, potentially. You never know. But yeah, if anyone has any questions or feedbacks or comments on this one, as we try to improve our disease detection algorithm, please let me know. Wow, my session crashed. Oh no. That's not good. Well, maybe I should get Colab Pro, don't you think? Well, let's just try it again and see if it works this time. Just restart and run it all again. Maybe next time I'll do it on my computer. My computer has more RAM, I think, than the Colab notebook. Let's see how much RAM they gave me. 13 gigabytes. That's actually a lot of RAM. All right, fingers crossed. Hopefully we can see it this time. You never know. Let me see if there's another alternative we could maybe use if this doesn't work. Oh, I have a question. What do you think about LLMs? I think you mean large language models, like maybe. Yeah, I mean, it's certainly interesting technology. you know, the one thing about those is a lot of them are not constrained. So if you have an output, you don't know if the output satisfies what you're actually looking for, if it's accurate in a sense. So I think people often overlook that. They don't really think about the fact that it's not a constrained model in a lot of cases. But otherwise, it's very cool, very cool stuff. And then you can do through custom tkinter. That is true. So if you would like to do tkinter, that is another option for Python. Absolutely. Absolutely. Wow, this iNaturalist module is really not making my Colab notebook happy. That's super unfortunate. It seems like we might need to abandon that and just use our ImageNet module. But one last thing that I wanted to try is changing from gradient descent optimizer to AdaGrad optimizer. So when you look up gradient descent in our notebook, you can see we're using tf.train AdaGrad optimizer. And instead of using that, I want to try and use the AdaGrad optimizer that they suggest in the notebook. So let's try that. This is the code for the AdaGrad optimizer. I think this should work. So let's see if we can get this one to go with the AdaGrad optimizer. I think we may not be able to use this minimize method with the AdaGrad, but we'll cross that bridge when we get there. Seems like it's working well enough, actually. We'll see in a minute whether it gives us any improvement on our gradient descent optimizer. We're just using a different optimizer, which allows us to sort of weight different aspects of weight different features in the decision. So at the gradient descent, you just kind of are considering all the dimensions and trying to optimize. So let me show you this actually, so that we can talk about the AdaGrad optimizer. I wish there was a good animation that I could see. If anyone has a good animation for this one, but basically, it allows you to have an adaptive learning rate, which is why it's called ADA for adaptive. And what that adaptive means is just, like I said, it's updating the weights of the different dimensions, treating them differently instead of the gradient descent optimizer, which by default treats them all the same. Someone says, wasn't able to speak till now, watching, but the session's been great, super lovely. I'm super glad to hear that you've been enjoying the session. Thank you for the feedback. I'm glad you were able to get your laptop. Welcome, and thank you for joining. Thank you for joining and watching and listening. It's really, really great to see folks interested in this kind of stuff. Actually, I think the Ada Grad Optimizer, we could probably say did in fact improve on our results. I think we got now almost 95% accuracy for one of our trains, and we converge around 94%. So 94, 95%. If you look at our confusion matrix, this is kind of interesting, actually. Now the best is leaf mold. Leaf mold has a 98%. But tomato mosaic virus being now often mistaken for leaf mold. So kind of interesting thing to think about. Now our algorithm's kind of calling everything leaf mold in a sense. But like, look at all these leaf mold, but none of these are leaf mold. Still, the overall, the accuracy of the models is a lot better. And if you're looking to eliminate all of the leaf mold in your garden, you definitely want to use this algorithm and not our other algorithm, because it's going to catch. If it's leaf mold, 98% of the time it's going to catch it. So that's a really, really good model for leaf mold. And Tanya Chen says, my final year paper is about heart disease detection using ML and IoT. That's really cool. Have you considered what algorithm you might use for that one? I'd be really curious to I hope your project goes really well. I'd be curious to learn more about it. But yeah, there's so many different applications of machine learning, and we can apply machine learning to have impact on natural environment, on disease, heart disease, plant disease, all kinds of things. And I hope that this workshop was able to, this workshop series really was able to help you improve with that. Now, if you ever want to do a computer vision project, maybe you have some starting points to get started with that. So everyone, this is sort of the last thing I had planned for today, kind of a shorter session for our last session together. I always try to make that one a little bit shorter because I know people might be getting a little bit tired after the third session. But yeah, I'm glad it was interesting to you all, and I hope you have a great rest of your Global Hack Week. As far as an ML roadmap, someone asked about a ML roadmap. I think it really depends on what you want to learn. We have a lot of really good workshops from February that you could watch on our website. February was Global Hack Week. The theme was machine learning. So I would recommend starting there and looking through some of those videos. But thank you, and have a great rest of your day.